Hey folks, I'm Demotro, and this is the Harmonic series, where you take the reciprocals of all the whole numbers from 1 upward and add them up indefinitely. And this is my casual way of writing that it diverges to infinity, or approaches an infinite size. And although that's a fact that mathematicians agree on generally, it seems like a lot of people in the public doubt that fact, because I made a short video on this channel which noted how a lot of people doubt this, so I'll include a short classic proof of the fact. And even with that proof, tons of people disagreed and said that I was lying or that I was wrong in some way. And the way that people thought this wasn't true had a lot of variance. It was kind of funny how varied the types of misconceptions people seem to have about this series are. And so in this video, I figured I'll answer a few seemingly common misconceptions about this series of various sorts and add some extra fun facts about this classic gem. Now, one of the common misconceptions that I saw in some comments on that video is people saying, well, infinity is not a number. You can't treat it like one. And that's sort of wrong and inapplicable to this in different ways. It's sort of wrong because in many fields of math, infinity or infinities are treated as a number or numbers. There are many fields where, although it would be written with a different symbol or symbols than that typically, where an infinity as a type of number is a used and accepted concept. But even with that, it's sort of not applicable to what's going on here, because we're using infinity more in the form of a limit. And we could actually define this fact without needing to use infinity as a concept. We can say that a series that I'm going to say diverges to infinity is exactly the type of series that for any number you pick that's any size of finite number, there will be a point where this series is larger than that number you've picked. A finite point in the series. And even if you pick some bigger and bigger chosen number, there will be some finite point where this series is larger than any finite number you could have picked. And so without even using infinity as a concept, if that's what makes some people uncomfortable, you can think of this fact as being that this will pass 100 at some point, this will pass 1,000 at some point, and so on. Now, another misconception about this for people who do believe that you could approach infinity with a series that has an infinite amount of terms allowed is that, well, you have an infinite amount of terms, of course it's going to approach infinity. Anything with an infinite amount of non-zero things added up will be infinite, some comments say. However, there's a classic series that I guess these people didn't encounter, but I feel like many people have encountered and maybe forgotten about, which is the concept of, let's say I have some distance, and we'll call that distance here 2, because that's what it's going to turn out to be. And let's say I go halfway toward that distance. Well, going halfway toward that distance means that sector I've traveled is 1, but I am going to write it as 1/1 to be similar to that. Now let's say I go halfway more toward the distance. Halfway more should be a distance of 1/2, half as much as that first distance was. Now let's say I go halfway more, that distance will be 1/4, assuming all of this that the full amount was 2. Halfway will be 1/8, 1/16, and so on. And we know that if I go halfway and halfway and halfway and halfway toward there, I'm never going to pass there. And in terms of numbers, what this tells us is that 1 over 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 would be next, and then the further powers of 2 never gets larger than 2. This series, we can say, approaches or converges to 2. Now, this would be written in a more technical way than my little arrows here, but the important true mathematical concept is that this is not a divergent series, even when we take it as an infinite series with an infinite amount of non-zero terms we're adding. None of these future reciprocals of powers of 2 that these turn out to be will be a zero amount, and we can add an infinite amount of them, but it's essentially going halfway and halfway and halfway toward that wall that we're not going to pass. And we can say that this series converges to 2 because although it never passes 2, it will get arbitrarily close to 2. No matter how small of a minuscule positive fraction you can pick, it will get that close to 2 and closer at some point. Sort of like a flipped version of how we could define this as it will eventually be larger than any finite, even massive number you pick. Here we can note that it will just get closer and closer to 2, and no matter how small of a finite shred of a positive fraction you could pick, it will be closer than that amount to 2 at some point, without ever passing it. So this is a classic example of a convergent series that shows it's not true that an infinite amount of terms has to mean that you go to an infinite size. Now, the funny thing is that on the flip side of that, you get a completely different side of misconception, which is people who remember this series too well, and they say, when referring to this harmonic series, like as a comment on that short I made, and say, nope, that adds up to 2. A lot of people commented, nope, no matter how long you take that, it approaches 2 without passing it, probably remembering this from somewhere and confusing it with that. But the funny thing about that is they obviously haven't thought about it for very long, because if you add up just 4 of the terms, these first 4, 1 over 1 plus a half plus a third plus a fourth, are already larger than 2. So obviously the series gets past 2. It does it pretty quickly. So to people who think that this approaches 2, I'm pretty sure this is the reason that they were thinking of that one. Now, even amidst those misconceptions or beyond them, people who do understand that this harmonic series gets bigger than 2 and do understand that there's not an if and only if connection between whether there's an infinite amount of terms and whether the size is infinite, a lot of people still do think that, well, this series shrinks at a fast enough rate that it seems like it's not going to get there. Even if it does pass 2 at that point, it does take a while to pass other integers. Here, for example, I have how many terms it takes to pass certain integers. To pass a size of 2, the harmonic series, you need to add 4 terms like we showed. To pass 3, you need to have added up through 1 over 11, the first 11 terms. To pass 4 takes 31 terms, 5 takes 83 terms, and here I jump forward to 10, which takes 12,367 terms. Then you can hop forward to 100, let's say, and it takes that many terms. I don't even want to count how many digits that is, even though I did spend the time writing it down, because that is exactly how many terms it would take the harmonic series to pass a size of 100. And if you were a mathematician back in the day who didn't really think through trying to prove this and just went at it with brute force, you probably would have given up even before that point and assumed that, well, even if it gets to 100, how's it going to get to 1,000? It took longer to get to each level here than the next because we're adding up smaller and smaller things. So it's going to take longer and longer to get to each finite chunk. How could it get to an infinite chunk? But despite that, you can look up lists of which massive number it passes 1,000 at. And there's massive numbers where it does pass 10,000 and onward. And any finite size, despite its slow pace, it does pass. And you wouldn't want to try and show that through brute force, because not only will that just never work when trying to tackle an infinite size, but in this case, it'll take a really long time to even prove the next time it passes, say, the number 101. So how would you go about seeing whether this diverges to infinity, or trying to maybe prove that fact? Well, let me go through a slightly more detailed version of the proof that I did put in the short I made. That is such a classic proof. It's an often used one when trying to explain how or why we know that this is divergent, because obviously we don't know that fact from checking a ton of numbers. We know that fact from a variety of proofs, and arguably the simplest one is the one I put in that short. So I'm going to reiterate that one here to make sure the details about it are clarified. So what we're going to do is, under this series, write a second series. And then we are going to compare the size of this and the smaller one. But at each point when designing this new smaller series, which must itself with an infinite amount of terms either be some sort of convergent or divergent. Some series follow strange patterns, but we'll make this one pretty linear and easy to follow. And what we're going to start with is taking 1/2 down here and noting that this term up here is bigger than that term down there. Now, what we're going to add here is 1/2 again, and we can keep a similar rule where we've noted that this term it's equal in this case, but is at least as big as the lower term. So far, all of the upper terms, compared to this thing I've circled there, is at least as big. Now, down here, I'm going to write 1/4 under the next two. And it's still following that rule, where each of the upper terms is at least as big as the corresponding lower term, right? Lined up with it right there. We had 1/3 is at least as big as 1/4, 1/4 is at least as big as 1/4. And now what we're going to do is go to 1/8. And we're going to fill that in until the number 1/8 right there, which will be 4 terms down the line. The amount we need to add if we're going up to the one that matches, so not to have any points where this lower one is larger than the upper, then we're always going to have a power of 2 distance to the next one that matches. In this case, 4 times we'll add 1/8 before we get to the one that matches. And then from there, we're going to add 1/16 8 times. And that'll get us to the one that says 1/16 up there. Then we will add 1/32 16 times, and so on. So that's the rule for our lower series. So Now let's note that this is 1/2, this is 1/2, this block of the ones with 4 in the denominator, add to 1/2, 2 times 1/4. This block with 8s in the denominator, add to 1/2, 4 times 1/8. The next block will add to 1/2, so will the next. Anytime we made one of these blocks, the denominator was some power of 2, and it was the previous power of 2 amount of them, leaving us them adding to 1/2. Now, since we're continuing this indefinitely, we're going to have 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2 as a way of expressing this series. The 1/2s will get further spread apart, but there always will be another, like there's always another power of 2. And if there's always going to be another 1/2 to add here, it's pretty easy to see that this lower series must diverge toward infinity, because it can be expressed as an infinite amount of 1/2s added up. And that's a number that doesn't even shrink. An infinite amount of 1/2s, most people will agree, would get to something we could classify as infinity, or at least use in that definition of it will pass the size of any finite number you pick. But we noted that the upper series at every point had every corresponding term at least as large as the lower. And if this series passed every finite number, and up to the point where it passed that number, every term in the top series was at least as big as the one in the bottom series, the top series must also have passed that number. Even more so, because some of the terms are larger than the lower series. And so if we ever have an infinite series that we know diverges toward infinity, and there's another infinite series that at every point is larger than that one, we'll know that that one must diverge to infinity as well. Now, you do have to be careful when playing games with infinite series. There are other ways that people try and rearrange terms in series to prove things that shouldn't always be considered proven, or to do silly things and get crazy results. So there are things you can't do when analyzing an infinite length series. But all the math here is airtight. It's a classic proof that I'm not the one who invented. I read about it and I have seen it other places in the meantime. It is a classic because it's a relatively simple proof for the fact that an infinite thing that goes really slow approaches an infinite size, which is pretty neat. Now, that to some people would be the end of the story. Okay, that's 2 infinite series. How many infinite series do I need? But really, it's just the beginning of the story when you consider that 1/1 plus 1/2 plus 1/4 plus 1/8 and etc., which in this case we're just adding one of each of these. That original one we compared to going halfway toward a wall. We're not adding whole chunks of them in that same fashion. This one we noted converges to 2. And this one we've seen diverges to infinity. So it makes you wonder, what other series diverge, maybe in an unexpected way due to their slow rate of growth? What other series converge to certain values, such as integers, or such as a fun one that also came up in another one of my shorts a while ago, which is that if you take the reciprocals of the square numbers, 1/1 squared plus 1/2 squared, 1/4 there, plus 1/3 squared, which is 1/9, and continue that forever. It does not diverge to infinity. It has one of those values it converges on, meaning that it will never pass that value, but there will be a point that it gets closer to that value than any shred of a fraction you could pick. And what that converges to is pi squared over 6. And really this, as well as this harmonic series, are two slices of this thing called the Riemann Zeta function, which is at the heart of a $1 million problem in math. Literally, you will literally get $1 million given to you if you submit a thorough enough proof of this thing called the Riemann hypothesis, which I will have an episode about in grade -2 at some point, as well as an episode in general about what other wacky values we might have with a series of an infinite amount of fractions added up. And what other series go at a very slow rate, perhaps even slower than this one grows, yet still also diverge toward infinity. It's a very interesting rabbit hole that we will have at least those 2 episodes about, if not more, related to during grade -2, which is coming quite soon. On the main channel, there will be a new episode about math and language related things coming out tomorrow on Thursday. There will also be, later in this grade, a final exam of sorts, although it'll be very different than tests that you're used to. And trust me, I'm not a fan of how tests are implemented in our society. This will be different and fun and worth it. And that will be the next episode on the main channel where I present that. And then there will be a very epic finale, including things like a field trip, maybe even a rare sort of camping trip, maybe certain sorts of reset ritual toward the modular cycle becoming the next grade, among other fun things, also including a shout out to all of my awesome Patreon supporters who have been super helping me with the job transition I mentioned in the other bonus video. And thank you all to those people especially, but to all of you viewers, and I will catch you again soon.